daughter is in Hyderabad, but son-in-law is in Bangalore.
Then my work from home.
Oh, work from home.
The limited of that function. So,
Okay.
the younger daughter is in Inaugural. So, she joined in the Infosys. Infosys has a branch in Toronto. Yeah. They have branch in Toronto, but not in Kochi.
Oh, okay.
IBM and TCS, they have branches in Kochi.
Oh,
Infosys.
oh, I see. What does she do?
She's basically a IT course. The other day, the elder is data consultant. She basically doing some tax job.
Oh, so both are doing something with this.
The younger one is basically supporting staff kind of that, not very technical. Not very technical. She knows supply math or other things of this thing. Good.
Okay. Can we copy the file now or we should wait?
You can copy it.
We can copy the file? Yeah. You can use this. I will show you the file.
Yeah.
We can copy the file.
So, why did you ഓൺലൈൻ ടെസ്റ്റ് ഉണ്ടാവില്ലേ എല്ലാവരും ഓൺലൈനിൽ ഞാൻ തന്നെ ഇദ്ദേഹത്തെ മീറ്റിംഗ് ആയിരുന്നു പക്ഷേ ഞാൻ കഴിഞ്ഞ ആഴ്ച മെസ്സേജ് ടോപ്പ് കൊടുത്തു വരാം തിങ്കളാഴ്ച ഇവിടെ ഡിപ്പാർട്ട്മെന്റിൽ ഉണ്ടായിരുന്നു അതിന് ടോപ്പ് കൊടുത്തു പോയി
We can put it. So
your next one is to so you are coming basically for the coaching program only?
Because it's at an awkward time. Our semester when Sridevi asked, I said, okay, I will come. I think our teaching goes to December 10th.
Yeah.
So what I did was I asked the registrar's office to fix the exam on or before 13th. So 13th evening if I leave, I will be in Cochin by 15th. Then 16th, 17th I can leave on the 18th afternoon from Kochi to Bombay to... but right now there is a problem because I booked Toronto, London, Bombay. Bombay, London, Toronto. But London to Bombay to London, both flights are cancelled.
Okay.
So they are saying that we will rearrange your travel and let you know. I am waiting. I just got about last week. I don't know what happened, why they cancelled. I think maybe the gas shortage. This is by Air Canada. Many of the flights, international flights. That's now they have to do that because what they have to do now is
Kochi to instead of going to Bombay, Kochi to Dubai or Abu Dhabi.
actually that's what I wrote to them, Air Canada. Instead change my flight from Toronto to Dubai to Kochi.
Yeah.
Then I can go from Kochi to Dubai to Toronto. That will be easier.
Yeah, you will not lose much time also.
That's what I have written to them. I have to see what they say. But the Air India, this is the third time the flight got cancelled. See, the problem for me is Air Canada has no association with the Emirates or Qatar. So they have partnership with the Air India. So they always direct you through Air India. Most of the flights.
So you are some point, so would you prefer the Air Canada?
No, because the Air Canada is leaving conveniently and coming back.
Okay.
So it's convenient for me, that's all. The points don't matter, but that's not the end. So I may have no other choice but to do this. Just to get them to take me to Dubai, buy a separate ticket from Dubai to Bombay by Emirates. Then from Toronto to London. No, they also have a flight to Toronto to Mumbai or Toronto to Delhi, but they operate only in certain months. Like in the summer, they don't operate all the time.
Oh, there will be another problem also with this winter issue.
Sorry, the fog. So Delhi, they don't
Delhi,
go.
Delhi, it's not
advisable. I once went to Island Kanpur and I got stuck in Delhi for 3 days.
The way these facilities are online, many people are doing online instead of mixing is very difficult.
I also think, maybe in both fashion, I also think that an in-person meeting is good.
Yes,
You also have meet people, you interact, that's all important. But that is lost in this online meeting now. More people in-person meeting. Hello? Oh, I don't, please, no need for that, no need for that.
We call it.
I will take, is there a program book?
I'll take that.
I will take that, that's enough, no need for that. You can give it to some school. I can open a shop of.
So, Damka, shall we sit over there? Starting the announcing.
Good morning, everyone. A very warm and cordial welcome to this auspicious inaugural function of the 11th International Conference on Recent Trends in Statistical Theory and Applications, organized by the Department of Statistics, University of Kerala, as a part of National Statistic Day Celebration 2026. This conference is jointly organized in association with the International Statistic Fraternity, the Indian Society for Probability and Statistics, and the Kerala Statistical Association. We extend our heartfelt welcome to all our distinguished guests, eminent statisticians, researchers, faculty members, students, delegates, and participants joining us both physically and virtually from different parts of India and abroad. Ladies and gentlemen, let us now begin this solemn function by invoking the blessing of the Almighty. I request Sony to lead us in the prayer.
Invite the dignitaries.
നെന്മയാകുന്ന കാന്തി കാണുവാൻ കണ്ണിനാകേണമേ നല്ല വാക്കിൻ്റെ ശീലം ചൊല്ലുവാൻ നാവിനാകേണമേ സ്നേഹമാകുന്ന ഗീതമോ എൻ്റെ കാതിനിണയാകണമേ സത്യമെന്നുള്ള ശീലമോടെ ഞാൻ ശാന്തി അറിയണമേ. ആ
To formally welcome the gathering, I now invite Dr. Shubha R. Nair, Professor, Department of Statistics, HHMSPB, NSS College for Women, University of Kerala, and Executive Trustee, International Statistics Fraternity, to deliver the welcome address.
Thank you. Good morning, respected dignitaries, distinguished guests, dear colleagues, students, and friends. Today, I am bestowed with the honor of welcoming you all to the 11th International Hybrid Webinar on Recent Trends in Statistical Theory and Applications 2026, that is WSTA 2026, in conjunction with the 10th Annual Convention of the Statistics Fraternity Kerala and the National Statistics Day Celebrations 2026 of our department. This workshop is jointly organized by the International Statistical Fraternity ISF, the School of Physical and Mathematical Sciences, the Department of Statistics, University of Kerala, in association with ISPS and Kerala Statistical Association. We are delighted to host this 2026 edition of WSTA in the hybrid mode so as to ensure the participation of those within and beyond the state as well as the country. As we all know, such conferences and workshops provide a global platform to exchange ideas, to foster collaborations and showcase advances in statistical theory and applications. Over the past 11 years, ISF, hand in hand with the Department of Statistics, has been successfully conducting such conferences, webinars in every July and international conferences in December, to ensure that we are able to bridge the gap between theory and statistical practice and to drive innovation that address real-world challenges across the various fields of statistics. These events over these many years have brought in the great minds of statistics, inspiring and motivating the academicians and students in our department as well as outside our department, and has helped in expanding their horizons. Moreover, this workshop seeks to honor the enduring legacy of the great eminent statisticians of our country, Professor P.C. Mehalanobis, Professor C.R. Rao, Professor K.C.S. Pillai, Professor K. Kalyanaraman, and Professor T.S.K. Muthada, whose pioneering work is commemorated through the various awards instituted in their names. Let me now proceed with my responsibility of introducing today's dignitaries and welcoming them. Let me begin by welcoming the guiding light, the force behind ISF, behind WSTA, behind ICSTC, our dear Professor C. Satish Kumar sir. He is the professor in the Department of Statistics, the director of the School of Physical and Mathematical Sciences, the convener of this conference, and the chairman of ISF. His boundless enthusiasm, steadfast resolve, and indomitable spirit have transformed these initiatives from vision to reality. Each milestone that we achieve here today bears the imprint of his commitment and his tireless effort. We welcome you with deep respect and affection, dear sir, and we look forward to your presidential address. It is our distinct honor to present the guest of honor of the day, Professor N. Balakrishnan, Distinguished Professor, McMaster University, Canada, who has kindly agreed to inaugurate our webinar as well as deliver the inaugural address. We have been fortunate to benefit from his expertise during the pre-conference workshop also, and Professor Balakrishnan sir's pioneering contributions have helped shape contemporary statistics and provide a benchmark for the various researchers worldwide. A long-standing friend and well-wisher of our department and a cherished presence in our academic programs, his participation brings both prestige and inspiration to this program. We welcome you with great esteem, dear sir. We are equally honored by the presence of our dear Professor Kalyana Raman sir. He has joined us online. Of course, it doesn't need any special introduction to our group. An eminent statistician, our a retired professor of our department, he was the one who brought computing into the department, which actually paved way to its current success. He was a visionary. He's a blessed presence in our programs and a revered guru to all of us. It is with profound respect that I invite you, sir, to offer your felicitations. Joining us to share felicitations is dear Professor P.G. Shankaran sir, who is the President of ISPS, the former Vice Chancellor of Cochin University of Science and Technology, former Professor of the Department of Statistics, Cochin University of Science and Technology, and actually my guru. A distinguished figure in the statistical community, and his presence adds special significance to today's proceedings. We are pleased to have you with us, sir, and a hearty welcome to you. The success of an event of this magnitude rests upon the generous involvement of eminent professors and distinguished researchers from around the globe who have graciously consented to enrich this platform by sharing their scholarly work. We are also privileged to host a vibrant cohort of students from India and abroad who will be presenting their research in the various contributory sessions, and we have got very enthusiastic participants in our various award competitions. To each and every one of you who have gathered here, directly as well as online, I extend a very heartfelt welcome on behalf of the organizing committee. I would also like to extend a warm welcome to the members of the organizing committee, to the advisory committee members, the distinguished office bearers of ISPS and KSA, to the faculty, staff and students of the Department of Statistics, University of Kerala. Last but certainly not least, I would like to extend a warm welcome to Dr. A. Riaz, Organizing Secretary of the workshop and Treasurer of ISF, who will be delivering the vote of thanks today. I also wish to place on record at this moment our sincere appreciation for the wonderful manner in which he has coordinated this event. Welcome to you, Riaz. Workshop like this strengthen our academic fraternity and integrate theory into the real world applications. When we begin this inaugural session, I hope the deliberations over the coming days will spark new research ideas, foster further collaborations, and deepen our collective appreciation of the subject and its various applications and various fields. On behalf of the organizing committee, I once again extend a warm welcome to all our guests, our delegates, our faculty members, researchers, and students who are joining this program. Thank you all once again, and I wish all success to WSTA 2026. Thank you.
Thank you, Madam, for the warm and gracious welcome. May I now request Professor C. Satish Kumar, Department of Statistics, and Director, School of Physical and Mathematical Sciences, Convener of International Statistic Fraternity, to preside over today's inaugural function and deliver the presidential address.
Honorable Chief Guest, Professor N. Balakrishnan, McMaster Distinguished Professor, McMaster University, Canada, and a great personality in the domain of statistics and related areas. Especially, I call him Vyasa. Like in the Mahabharata, we have the Mahabharata-like books in statistics. So every department in the world, or related departments, they have the library. In the library, there are books on distribution theory, the continuous, discrete, volume 1, volume 2, like that, multivariate, etc. In which the present giant of the world, in fact, Professor Balakrishnan. Johnson, Codson, Balakrishnan. So Balakrishnan is the major of that. So I'm very much glad to be Professor, who agreed to give keynote talk at this conference. Plenary speakers, there are keynote and plenary speakers. There are several in the online way. and respected Kalyanaraman sir, our Guru, and he is always with us for whatever we are doing, whether it is via online or offline. He is always a lighting force to us. Professor Kalyanaraman sir. Professor Shankaran is familiar to all of you. Is a former Vice Chancellor of Cochin University of Science and Technology. More than that, he is a very passionate and dedicated teacher in statistics and researcher in statistics. And presently, he is the president of the Indian Society for Probability and Statistics, of which I am also belong to that as the executive committee at present. And eminent statisticians from India and abroad, especially Professor Vishwanathan sir, he is from Chennai, taken greater pain and come over here and encouraging our these types of ventures. Professor Dr. Nawaz is in fact in the RBI representing, but now he is outside Kerala, Doha, outside India, Doha or something, isn't it? Yeah, he is leading one of the statistical group in a bank, public bank, limited bank. There, and several distinguished guests on and off the, in fact, online as well as offline. They agreed to meet. And Professor Prabhat Chaudhary from Delhi University, he will, he promised me to join before 10, but some problem, I think, please, some volunteers, please help him in case he need any help. So he promised me, no problem, I will reach there, whatever. Professor Kishore Kumar Chaudhary, Majumdar, he also agreed to come over here. He is from ISI Bangalore. Even though he is not in he is a wheelchair person. He has given a talk yesterday in the workshop. He promised me, in fact, he is very much interested to come over here. And Professor Kishore Kumar Chaudhary and faculty members from various departments and universities here joined in the online, research scholars and dear students. Very good morning, good afternoon and good evening to all of you, because we are conducting both via offline and online. And happy National Stats Day. It is indeed my great privilege and honor to preside over the inaugural function of WSTA 2026. Even though we are a little bit late, we are starting a little bit late, don't worry about that. We have time, we arrange it in that way. So don't worry, we will be in the right time. And even though we find only few here, they are serious persons. Apart from the, in statistics we know, not much number will be, we have less compared to other disciplines. But there are more serious and more seriously that we need. On behalf of the organizing committee, I extend a warmest welcome to every distinguished delegates, to everyone who has joined both physically and virtually from different parts of India and across the world. This conference, organized in association with the Department of Statistics, University of Kerala, School of Physical and Mathematical Sciences, University of Kerala, the International Statistical Fraternity, the Indian Society for Probability and Statistics, the Kerala Statistical Association, coincides with the National Stats Day 2026 and the 10th Annual Convention of Statistics Fraternity Kerala, instituted by our former faculty members. It reflects our collective commitment in advancing statistical science through research, collaboration, and academic excellence. Friends, every conference disseminates knowledge, but only a few evolve into enduring academic movements. I am delighted that Over the years, WSTA has grown from the modest initiative into an internationally recognized platform where statisticians, data scientists, academicians, industrial experts, and young researchers come together to exchange ideas, establish collaborations, and inspire one another. This year, we are particularly fortunate. During the next 4 days, more than 150 eminent speakers, including 25 keynote and plenary speakers, and 90 invited speakers, will share their experience, expertise in diverse areas of statistical science. We are deeply honored by the presence of internationally renowned statisticians from leading universities and research institutions across the world, like Professor Barry Arnold, Professor Balakrishna physically with us, like in online, Professor Barry Arnold, Professor Kusubavisky, Professor Gauri Nanda, several, I'm not naming all. In the brochure or conference website, you can see several. And their gracious acceptance of our invitation is not only a privilege, but also a testimony to the academic credibility that this conference has earned over the years. Dear young researchers and students, today I wish to speak especially to you. The greatest benefit of attending a conference is not merely listening to lectures. It is the opportunity to interact with experts, exchange ideas, ask thoughtful questions, and build lifelong academic relationship. Every presentation you make, every discussion you participate, and in and every new contact you establish may become a milestone in your research career. Never underestimate the value of your first or the initial type research papers. They never hesitate to ask questions. Never be afraid of criticism. Every internationally acclaimed statistician who we admire today once began as a young researcher with curiosity, determination, and a dream. The future of statistical science will be shaped by those dare to think independently, work with perseverance, and uphold the highest standards of scientific integrity. One of the distinguished features of WSTA is its unwavering commitment to recognizing and encouraging young talent. We firmly believe that timely appreciation inspires lifelong excellence. With this vision, we have instituted several prestigious awards in honor of some greatest statisticians of our country, including Professor P.C. Mahalnobis, Professor C.R. Rao, Professor P.C. Mahalnobis Best Paper Award, Professor C.R. Rao Best Paper Award, Professor K.C.S. Pillai Best Paper Award, also along with several other awards, Professor K. Kalyan Raman Best Project Presentation Award, Professor T.S.K. Mutad Memorial Quiz Competition Award, like that. Besides several endowment lectures and recognitions. These are not merely awards. They are our investment in the next generation of statisticians and researchers. I take this opportunity to express my heartfelt gratitude to the distinguished statisticians, alumni, institutions, and generous well-wishers whose support has made these awards and endowments possible. Their contributions have encouraged countless young minds to pursue research with greater confidence and commitment. I sincerely hope that many more alumni or well-wishers or philanthropies, academic institutions, industrial organizations will come forward in the years ahead to institute new awards, fellowships, and endowments. There can be no greater contribution to statistical science than inspiring a young researcher to pursue excellence. Friends, as we celebrate National Stats Day, we respectfully remember Professor P.C. Mahalanobis, whose visionary leadership transformed statistics into a powerful instrument of national development and evidence-based governance. At this moment, we also remember our deep respect and gratitude to our beloved teachers and distinguished statisticians, Professor A.M. Mathai and Professor P. Yagin Thomas, whose recent demise has left an irreplaceable void in our statistical fraternity. Both were constant sources of encouragement to our academic activities and passionate supporters of young researchers. Their scholarship, humility, generosity, and unwavering commitment to statistical science will continue to inspire us for generations to come. I request everyone to one moment for a tribute to these stalwarts. Thank you. The greatest tribute we can pay to these illustrious teachers is not merely to remember them, but to carry forward the mission to which they dedicated their lives, promoting research, nurturing young talent, and strengthening the global statistical community. With regard to those, we will honor them through workshops or conferences in the near future, incorporating great personalities. Before I conclude, I express my sincere gratitude to our chief guest, Balakrishnan sir, distinguished speakers, delegates, this organizing committee, faculty members, research scholars, students, volunteers, and every well-wishers whose wholehearted support has made WSTA 2026 possible. Let this conference inspire new ideas, foster lasting collaborations, nurture young talent, and contribute meaningfully to the advancement of statistical science. Allow me to conclude with a humble appeal. If every one of us leaves this conference having inspired one young researcher, encouraged one innovative idea, supported one deserving student, or instituted one award or endowment for promotion of statistical science, WSTA 2026 will have achieved far more than the successful conduct of an international conference. It will have strengthened the future of statistics itself. Let us work together to build that future. Also, I conclude with a thought that I firmly believe reflects the spirit of this conference. Research begins with curiosity, grows through perseverance, flourishes through collaboration, and ultimately transforms society through knowledge. With these words, I wish WSTA 2026 a very success and all participants a highly enriching, intellectually stimulating, and memorable conference. Thank you all. Thank you so much for it.
Thank you, sir, for those inspiring words. The most awaited moment of the morning has arrived. It is my great privilege to invite Professor N. Balakrishnan, Distinguished Professor, McMaster University, Canada, to formally inaugurate the 11th International Conference on Recent Trends in Statistical Theory and Applications. May I request our dignitaries on dais to kindly join the inaugural ceremony. Thank you, sir, for inaugurating the conference. May I now invite our chief guest, Professor N. Balakrishnan, to deliver the inaugural address.
Thank you. Thank you very much for the invitation. Thank you very much, Satish, for organizing such a nice event. It's great to see people. I noticed that more and more prefer online presence rather than in-person presence. I want to say that the in-person presence is always better. For example, I meet PG Shankaran after a long time. In online, you don't get this opportunity. So it's very nice. I am particularly pleased to see so many youngsters in the audience, and that's a good sign for the field. The field can develop only if you can inculcate what you learn into young people. So it's very nice to see all of you. Some of the faces I recognize from the workshop yesterday. So it's quite nice to see you all, and I look forward to a productive conference, and I hope all of you enjoy the conference. Thank you very much.
Thank you very much, sir, for your enlightening and thought-provoking address. We now move on to the felicitation session. I respectfully invite Professor K. Kalyanaraman, an eminent Indian academician, author, and retired professor from the Department of Statistics at the University of Kerala, to offer the felicitation.
Kalyanaraman sir, we can't hear you. Kalyanaraman sir? Maybe better to call, I think. ഫോൺ മൈക്കിൻ്റെ അടുത്തോട്ട് വെക്കട്ടെ? ഫോൺ മൈക്കിൻ്റെ അടുത്തോട്ട് വെക്കട്ടെ? സാർ ഫോണിലാണോ പറയുന്നത്? ഓക്കെ സാർ, ഓക്കെ, സ്റ്റാർട്ട് ചെയ്തോളൂ സാർ, കേൾക്കാം. സർ സംസാരിച്ചോളൂ, ഞങ്ങൾ കണക്ട് ചെയ്തു. Kalyanaraman sir?
Yes,
I'm here. Okay, so can you please start, sir, because
my connection is not.
Yeah, you can.
My connection is not coming in.
No, we can hear you over phone.
I can connect only through phone.
Okay, so shall we cut this call?
Yes.
Okay.
So can I?
Yeah.
Can I say? Can I say something?
Yes, please say, sir.
Huh?
Yeah, please continue. data.
Actually, he's connecting through his phone.
സാറേ ഇപ്പം പറഞ്ഞാൽ മതി ഞാൻ ഈ ഫോണേ
പറഞ്ഞാൽ
പറഞ്ഞാൽ മതി ഇപ്പം ഡിസ്റ്റർബ് മറ്റേ നെറ്റ്വർക്ക് അത് മതി സാർ പറഞ്ഞു
ഇത് കണക്ട് ചെയ്യണ്ട റൈറ്റ്
ഓക്കെ
ഓക്കെ
കേൾക്കാം
So, no, very sorry that the connections are not correct. So, I just take this small speech and just say a few good words. That's all. And I'm already weak. I'm not able to talk. So, it's a practice that senior teachers used to talk. So I just offer my congratulations to our students, and I'm really, the organizers are doing one wonderful job, and I have one more wish. The wish is we have to bring out the proceedings of this program. So I think it is the 12th year or 11th, 12th or 13th year. So some thousands of papers have been presented, and you can continue to do it, and all the efforts that we have made, this document will be an indication. So I thank you for making this possible, and I'm happy to see Professor Balakrishnan after a long time, and I wait for small speak that he is going to give. So I take this opportunity to congratulate every participant and every person who is responsible for this particular program, and try to continue the same thing for years to come. I hope that I'll be here for few more years. So thank you very much. And I wish the function all success. I'm sorry that I'm unable to speak as I used to talk. And at this stage, I think that this is only possibility. So thank you very much. Go ahead. Thank you very much.
Thank you, sir. Thank you, sir. We are actually blessed to hear your words. Thank you for your blessing, sir.
Thank you, sir. May I now invite Professor P.G. Shankaran, President, Indian Society for Probability and Statistics, former Vice Chancellor, Kochi University of Science and Technology, to offer the felicitation.
Professor N. Balakrishnan, Chief Guest of the Day, Professor Sadish Kumar, the Chairman of the Organizing Committee of this International Conference, and Dr. Riaz, Dr. Shubha, other distinguished participants, young researchers, faculty members, and my dear friends. I'm very happy to be here to see the young researchers as well as my colleagues and friends through online as well as offline. Okay, this is I congratulate the Dr. Sadish Kumar and his team for organizing such a conference. This is a continuation of a series of conferences organized by Dr. Sadish Kumar in collaborations with many associations in India and abroad. The basic idea of organizing a conference is to get a platform for young researchers to interact with the senior colleagues, senior faculty members and experienced researchers. But unfortunately, as mentioned by Professor Balakrishnan, most of the even young researchers, they would like to prefer online meetings instead of offline meeting. So I came here to meet Professor Balakrishnan and to present this particular inaugural function as well as giving a lecture in my area, and I hope that in future this conference should be arranged in offline, and basically offline conference, and online talks you can arrange even in week in every month or every week through different platforms that you can do. But the conference mostly may be arranged offline, and some of the speakers, maybe 2 or 3 speakers, they can give talks through online. That's okay. But otherwise, what happens is most of the people, they would request the organizer to have online presentation instead of offline presentation. And this is in connection with this National Statistical Day, and we always remember the great contributions of the father of Indian statistics, Professor P.C. Mahalanobis, and his wisdom and knowledge actually helped India to move forward during the independence period. One important thing you must, especially young researchers must understand that he was a physicist initially, then moved to another area, statistics, completely different in the sense during that period. Now the people are talking about interdisciplinary studies and multidisciplinary studies, but even though in 70-80 years back, many of our statisticians, they moved from one discipline, maybe in physics or mathematics, they moved to another area, statistics and related areas. So in the current context, you also try to move to different areas, because the subject has got a lot of challenges due to advancement of technology. You have to update your knowledge, update your new tools, etc., so that you will be surviving in the current world. I request all of you to explore this rare opportunity. I once again wish a very best to this conference. I congratulate the organizers once again for arranging this wonderful event. Thank you very much.
Thank you, sir. Ladies and gentlemen, as part of the National Statistics Day Celebration 2026, the Department of Statistics organized the Professor T.S.K. Muthad Memorial National Level Online Quiz Competition for higher secondary, undergraduates and postgraduate students studying statistics and mathematics. The competition witnessed enthusiastic participations from students across the country, reflecting their keen interest and aptitude in statistics and mathematics. We now come to the most weighted announcement of the results. It is my privilege to invite Professor C. Sadish Kumar to kindly announce the results of the Professor T.S.K. Muthad Memorial National Level Online Quiz Competition. May I request Professor C. Sadish Kumar to please come forward.
So, with a great pleasure, we announce the result of the Professor T.S.K. Muthad Memorial National Level Quiz Competition. In fact, we have conducted this quiz competition at 3 levels. One at higher secondary level, then graduate level, undergraduate level and graduate level. And we have several entries. And finally, the jury of the selection committee selected only the candidate who secured more than 90% in scored in so that the higher secondary level there were no one qualified. So we are not giving the award for the sake of award, but for encouraging the student. Undergraduate level, 2 candidates scored, and one from Miss Disha Ratnakar Pardeshi from Ferguson College, Pune. And another person at Sudapi Tripathi, University of Lucknow. At postgraduate level, Sambhavi Deshmukh, Savitripur Pune University, and Devika Suresh from University of Kerala. Congratulations to all winners. We are very thankful to all the participants, and we hope to have more such awards. And thank you all. Thank you.
Thank you, sir. May I now invite Professor Satish Kumar to honor our chief guest, Professor N. Balakrishnan. Sir. To propose the vote of thanks, I now invite Professor A. Riaz, Organizing Secretary, International Statistic Fraternity, Department of Statistics, University of Kerala.
Good morning, everyone. It is my duty to thank all the dignitaries present here today for making this event a grand success. First of all, I would like to express my sincere thanks to our chief guest and distinguished professor, Dr. N. Balakrishnan sir from McMaster University, Canada, for being a constant support to all of our programs and for inaugurating this conference. Now, I would like to thank our former professor, Professor K. Kalyanaman sir, who were kind enough to felicitate this event. On behalf of this organizing committee, I express my sincere thanks to Professor P.G. Shankaran sir, former Vice Chancellor of CUSAT, and the President of ISPS for felicitating this program. Now, I would take this opportunity to express my sincere thanks to Professor C. Satish Kumar, Director, School of Physical and Mathematical Science, University of Kerala, who is the main person behind this conference. Thank you, sir. Now, I express my sincere gratitude to Professor Shubha Nair, the Executive Trustee of ISF. On behalf of the organizing committee, I express my sincere thanks to the esteemed Professor Vishwanathan sir and Nawaz sir from RBI, and the other distinguished professors from the various institutions and teachers from the colleges, the research scholars, MSc students, and the online participants, and all the faculty of our department. Once again, thank you all.
Thank you very much. Ladies and gentlemen, as we conclude the inaugural ceremony, may I request everyone present in the hall to kindly rise for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभाशिष मागे गाहे तव जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे.
The inaugural session of the 11th International Conference on Recent Trends in Statistical Theory and Applications hereby comes to close. There will be a short break of 10 minutes. Kindly reassemble in the seminar hall by 11:15 a.m. The technical section will commence thereafter as per the conference schedule. Thank you and have a wonderful day.
Additive multiplicative rate model. എനിക്ക് ആരെ എൻ്റെ ഒരു പെൻ ഡ്രൈവ് എടുത്തു ഇവിടെ പോയാൽ പറ്റിയില്ല ശരി ഞാൻ എനിക്ക് അവിടെ കിട്ടി ഞാൻ അവിടെ വെച്ചോളൂ.
In fact, 11:20.
11:20, so we have time.
We direct them to 11:50, then only we will come.
It's okay, they can take their time. So, next Wednesday, coaching, yeah. I copy it. And copy it.
No, I think it may be for online, but I think they will hear.
So it's better to use mic.
Otherwise, online
people will not hear. And also, teacher etc. there is only.
Oh, okay.
Teacher from Hyderabad.
Yeah. Central University.
Because
Rao Institute.
yeah, Rao is yes.
Good morning, everyone. Distinguished delegates, respected faculty members, researchers, and dear participants, it is my great pleasure to welcome you all to the first technical section, keynote section of WSTA 2026. We are deeply honored to have Professor P.G. Shankaran, Cochin University of Science and Technology, as the session chair of this session. Professor Shankaran has served the academic community in several prestigious leadership roles, including Vice Chancellor, Pro-Vice Chancellor, Professor, and Head of the Department of Statistics and Director of the Center for Population Studies at CUSAT. His outstanding contribution to statistical science has been recognized with several prestigious honors, including the Distinguished Statistician Award from the Indian Society for Probability and Statistics and the Young Researcher Award from the International Indian Statistical Association, USA. It is equal privilege to welcome our keynote speaker, Professor N. Balakrishnan of McMaster University, Canada. Professor Balakrishnan is one of the world's most distinguished statisticians, widely recognized for his remarkable contributions to probability, reliability, order statistics, survival analysis, and statistical inference. He is a fellow of several prestigious international statistical societies and authored and edited numerous influential books and hundreds of research publications and has inspired generations of researchers across the globe. On behalf of the organizers of WSTA 2026, with great pleasure, I invite Professor P.G. Shankaran to chair the section. Over to you, sir.
Balakrishnan and other distinguished speakers, I'm really honored to be the chair of this first technical session of the international conference. And already the organizing committee member introduced Professor Balakrishnan and his contributions in statistics and related areas. And if you search in Google, you can see his list of publications and list of books published, etc. So that he doesn't need an introduction, especially his books on continuous distributions, discrete distributions, or multivariate distribution. We all familiar with these books, and you can see that those books were written by Johnson, Coates, and Balakrishnan. So, and we have collaborated in different ways, and we basically, myself, Professor Balakrishnan and Professor Unnikishan Nair, we published 2 books, one by this academic press, another by this Burkosar. 2 books we published, one in quantile-based reliability analysis and another in modeling and analysis of lifetime data in discrete time. So we have a collaboration, and basically I came for this conference to meet Professor Balakrishnan after a long time. Otherwise I would have also preferred to attend the conference through online. So this is a very good occasion to meet Professor Balakrishnan, and you can see that how he is handling the lecture. This is actually, you can, this will be definitely a model lecture for you, and we also grab some ideas of how to give lectures from him. So he will always say the full name of the references. We usually say Shankaran et al., but he says Shankaran and Professor Unnikishan Nair 1999, etc. So how to give lectures, you can see how dynamic when he gives lectures, that you also very much appreciable. On behalf of organizing committee, on my personal behalf, I invite or request actually Professor Balakrishnan to begin his lecture. The topic is already given here: statistical inference and Clark. Thank you very much. Yeah, thank you. Can you all hear? Yeah. So yesterday I conducted a workshop on reliability, and I talked about degradation modeling, which is one type. How many were you at the workshop yesterday? A few. I talked about degradation data. That's a type of data where you do not observe failure, but you observe that the quality characteristic decreases over time. It degrades over time. How to model that? I used a stochastic process, and then I showed how to make inference. Today I am going to talk about a different type of data. So I want to first start with the title and familiarize you with the topic. So that's the statistical inference. All of you know, you take a course, and likelihood inference, it's Bayesian inference, etc. And this is a new phrase. Many of you will not know what that means. You may know, if you work on reliability, what is ALT. ALT stands for Accelerated Life Testing. You may ask, what is Accelerated Life Testing? I mentioned briefly yesterday that units which live a long time, which survive a long time, do not easily fail. So testing them for their reliability characteristics is difficult. It takes a long time, such as refrigerators, TVs, etc. Their average lifetime may be several years. How do you test them? you do accelerated life testing. That means you find a stress factor, you increase the stress, observe the failure times at increased stress levels, then you come up with a physical principle to model the acceleration and the lifetime, and then you extrapolate to normal operating conditions. This is what is called as accelerated life testing. This goes back to about 60 years in literature. But I'm going to talk about a new accelerated life testing. That's why there is a C there. C means cyclical. So you accelerate, but it doesn't usually accelerated life testing like voltage, or you can use temperature. These are monotonically increasing. So you use link functions to connect them monotonically. But some life testings are not monotone in terms of stress. They are cyclical in nature, in which case the usual methods of accelerated life testing doesn't work. There are some thermodynamic principles I will talk about, coffin model, and how they come into picture for modeling, and I will talk about inference. So I'm going to take probably about 40 minutes. Whenever P.G. Shankaran says you talked enough, I will stop wherever I am. If any of you want to know further details, you can write to me, and my email is there. Okay, so this is jointly, it's a collaborative research with 4 of my students. They are all Chinese students, and they are all in different universities in China, and they usually visit in the summer. We work on this topic. Okay, I have published recently 3 papers on this topic, cyclic accelerated life testing, and I have given the references here. The Reliability Engineering and System Safety is the highest ranked reliability journal. So there are a couple of papers which got accepted in 2025 to appear soon. Okay, so you can always look in these journals and download the papers if you want original papers. Okay, what you are going to see in today's talk is, first I'm going to give an introduction because there are many students here who may not be familiar with the topic. So I want to first give an introduction. I will talk about what is accelerated life testing, what is cyclic accelerated life testing, and how to formulate the model. Then I will state what are our goals, objectives. Then I will talk about inference. There are different types of inference you can develop based on the data that's available to you. It's easy to start with a likelihood inference. You soon realize there is a complication with the model estimation because the number of parameters can increase depending on the number of covariates you have. So I will talk about best linear unbiased estimation, maximum likelihood estimation. There is also a problem of optimal design. How to design an experiment like I discussed in the yesterday. Then I can also describe a semi-parametric approach which I will briefly describe, then present the results of a simulation study, give an illustrative example that I will start with. So, what is an accelerated life test? Like I briefly stated, you want to collect sufficient information in order to make inference about lifetime characteristic of a product. But if the product is highly reliable, you cannot collect sufficient information in a reasonable period of time. So, accelerated life test identifies some key stress factors on the product, change the stress levels so that the units fail faster in a shorter time. You collect that information, then you extrapolate it to normal operating conditions. This is what is called as ANT. It allows you to collect sufficient information effectively in a short period, and that's important. So you cannot go to the manufacturer and say, I will do a reliability test on the TVs that you produce, but I need 10 years. they will fire you before that. So you need to conduct these experiments in a shorter period of time and collect information and make some prediction at normal use. So cyclic accelerated life test, on the other, accelerated life test started its work in 1960s from Russian researchers. And a cyclic accelerated life test acts with cyclic stress, like for example thermal cycle. Thermal cycle can increase, decrease, oscillate, stay constant, etc. So this is cyclical in nature, and that creates special problems in modeling. And there is a book by a mechanical engineer, Purdue University, by Young in 2007. Okay. So here is an illustrative example that I have given. You look at this experiment here. What do you have? I have a temperature, which is the stress factor, and I am observing over the time on the horizontal scale. I have, for example, the T min, which is the time, and T max is the maximum time. And you notice that the stress takes place, but it takes place in a cyclic fashion. It goes up, stays constant, it comes down, stays constant, and it goes up. It can repeat this process. This is not a monotone accelerated life testing. If you look at the book by Wayne Nelson on accelerated life testing, most of the experiments are monotone. This is a non-monotone stress factor. And this period where it stays constant is called the dwell time. Then this is called the ramp rate. It ramps down. Then you have a dwell time, and then this is a ramp up. Ramp down, ramp up. So you do the testing on the units with this scheme. You collect data. So here is the data that I have given. There are 8 units being tested. F is basically the frequency at which the data are collected. Delta T corresponds to the difference in the time. 120K, 100K, 100K, 120K, etc. You notice these delta T's are not monotone like in the usual ALT experiments. And the T max is the maximum time that you can test these units at these stress levels. So for example, at 120K, I cannot do a test beyond the time 300 and beyond 393K. So this is a nature of data that you have. We have to model this. And not only we have to model this, we also collected data. We have to figure out how to make inference for data that you have observed. Okay. So how to analyze lifetime data from such experiments is the question. I think there is something hidden. It's okay. It's okay, no worries. Yeah. There is a bottom message, I don't know what it says. Stop sharing or hide. Maybe you have to press hide. Okay, doesn't matter. So, the first model that was introduced is what is called as a Coffin-Manson model. These are all engineers, they are not statisticians. So, Coffin and Manson introduced this model in which they said M is in the form power law model. There is a slope which is unknown. Delta T, notice the data here, delta T is the difference in temperature and to the power minus B. So it's a power law model. And I will explain what these are. The other model is called Coffin-Manson-Arrhenius model, which, this is given by A delta T to the power minus B, same, except there is a nonlinear function there, which is the function G. It's a function of maximum time as maximum temperature, not time, maximum temperature as well as active energy. EA is nothing but activating energy. Then the third model is called Norris-Landsberg model, which combines the two, so it's like a nested model. which is nice for us, because in statistics, one thing you learn is if you have a nested model, you can do hypothesis testing. So you start with a general model and ask, is the simpler model itself would suffice to analyze the data? And that is why this nested model scenario is very convenient. So the Norris-Landsberg model, you see that it has the same, except there is a f to the power minus a, and so that a equal to 0 will correspond to the simpler model. So these are the things. What is n? N is the number of cycles to failure. How many cycles the unit went through at that temperature before it failed. Delta T is the change in temperature, which is in your table before. You see, this is the change in temperature. How many cycles the unit has to undergo before it fails is what you collect as the data. And F is the frequency applied to load, usually measured in hertz, and the G function is just a parametric function, which is a function of active energy. K star is the Boltzmann constant, T max is the maximum of the temperature at that particular time point. So this is a model. What the mechanical engineers, for example, what Professor Yang at Purdue University does, is they treat this entire function to be a fixed function. The parameters are experiments are conducted and they fix the parameters as fixed constants, and they don't treat them as estimated from the data. So this is where the statistician can play a role. So model formulation. What I'm going to do is take those models, I'm going to twist a little bit to make it convenient for statistical inference. So n is the number of cycles, I'm going to normalize it, because f is the frequency applied to load. Since the frequency changes, you cannot just treat n to be a homogeneous random variable. So I'm going to take n divided by f. That is my new random variable y. It's a normalized load to failure. So cycles to failure. And I introduce randomness in this particular way. I take expected value of yi divided by expected value of yj. Think of two units. If I take their proportional expectations, then I come back to this function, Norris-Landsberg model. I will have two functions, one for ith unit, one for the jth unit, and I relate it here. So I have fi, ti max are related to the ith test environment. Then I accelerate the testing environment by SIs. SIs need not be monotone. In the usual accelerated life testing, it's monotone. Here, the stress depends on three quantities, not just one variable. One is how much of frequency you are using. Delta Ti is how much of incremental temperature you use, and what is the maximum temperature you can use at the ith stress level. So there are three. And then what I do is I collect data. The observations can come in different forms. For example, if I test Ni units at the ith test environment, there are several test environments, capital I. In the ith test environment, I will test Ni units and I can observe all the failure times, which is called as a complete data. Or I can observe just a small portion of the data and terminate the experiment, which is called type 2 censored data. Or I can observe up to a certain time. I'm going to do the test for 160 hours. Whatever doesn't fail before 160 are censored, which is called type 1 censored data. These are the three common forms of censored data in reliability. So, what are our objectives? The objectives are to use the observed data from such a cyclic accelerated life testing to estimate characteristics of the lifespan, not at all stress levels. I'm interested only in operating condition. What is the normal stress condition? Because if I test, for example, a TV at a high temperature or high voltage, that's not going to be a common use. So you want to make inference under normal operating condition. And also to develop inferential methods. You can do many things concerning optimal design, quantile estimation, warranties, etc. So I have given the Norris-Landsberg model. You may wonder why I stick with Norris-Landsberg model, because that's the general model. The other two, Coffin-Manson model, etc., are a particular case. So if I deal with the Norris-Landsberg model, I can test whether the simpler models are reasonable and consonant with the data. So I transform the Norris-Landsberg model with a logarithmic transformation. I start with a y, take the log, and the multiplying constant will become an additive constant. Fi had a power comes down, log of Fi, etc. Now the only difference is this Norris-Landsberg model, I took a logarithmic transformation, there was no stochastic part in it. Now once I take the log, it looks like a regression model. So what I do is, I inject a random noise, and that is my error epsilon ij. And I say, if you do a testing of a unit at the same stress condition, it's not that they will fail exactly at the same time. Each unit has its own variability. So this epsilon is like a random noise, or you can say unit to unit variability within that stress condition. So immediately you can put a least squares type estimate, which is a crude estimate, but at least you know what to do. You go through the Eij as the error, you construct a least squares estimate, then it will give me how to predict the lifetime under normal operating condition. Normal operating condition is just one stress level. Once I estimate the parameters of this model, it facilitates me to predict at any stress level, including the normal stress level. So, limitations. The problem with this is unable to deal with sensor data and the associated inference. The regression setup works nicely with complete data, but it has problems in finding, for example, the estimation when there is censoring, and how to include the censored information into least squares is a problem. So unable to deal also with non-homogeneous variance of log of Yij. If I do the regression estimation, I have assumed that at the ith stress level, all units have the same amount of variability, the assumption of homogeneity, and it becomes difficult to accommodate a heterogeneity in the setup. So, it will naturally be of interest then to find suitable models satisfying the Norris-Landberg assumption that could also deal with sensor data. So there are two goals here. One is we want the Norris-Landsberg model, but how to adapt it so that we can develop a method of estimation to deal with sensor data. Why sensor data? Most reliability experiments result in sensor data because of limited time available to do the test. The manufacturers will not allow you to do the test for infinitely long period. So it's a limited time, so it's always a sensor data. So I'm going to start with a general family of distributions, shape-scale family of distributions. Shape-scale family of distributions are like gamma, for example, and Weibull. These are all shape-scale. It has a shape parameter and it has a scale parameter. So the ith stress level, I assume there is a shape parameter alpha and there is a scale parameter beta, and then we use log linear link function. The log of the scale parameter is connected in this way. This is where the log linear link function comes. But notice here that the beta i's need not be monotone, because these guys are not monotone. But we allow this log linear link function to capture the Norris-Landsberg model. So here the log linear link function is accommodated through Norris-Landsberg model, and that's the difference. So we could also use additive distributions. For example, we can take a gamma distribution with alpha I, beta I, where the link function you use is for the mean, log of alpha I, beta I as the Norris-Landsberg model. So there are different ways to model, just like different ways to peel an onion. You can take the same data, take the same model, but parameterize it in different ways. You can make inference. So what is the advantage of this? The second one has an advantage because it can accommodate non-homogeneous variance. Alpha I, beta I is the mean, alpha I, beta I square is the variance, so it allows for heterogeneity in the model, which we could not do before. So there are different ways in which we can do. Now I have to develop an inference. First I am going to start with a likelihood inference. So what are these? I am going to assume that I have this kind of, please note, G is not gamma. It is just any family of distributions which have a shape and scale parameter. So I assume Yij's are following from the distribution G, which are different scale parameters beta I, same shape parameter alpha, and the beta i's are log linearly related to Coffin-Manson model. And that's what I have, Norris-Landsberg model. So then the likelihood function is simple for complete data. If I have complete data, I can order them. There are ni factorial permutations of ni objects I can do, and then put the product of the density. And this is what we need to maximize. If you have a type 2 sensor data, then I will have ni factorial by ni minus ri factorial. Ni minus ri units, all I know is that they are alive at the end of the time study. So they will have a survival function to the power ni minus ri. If it is a type 1 sensor data, it is the same, except the number of failures you observe is random. So the three likelihood functions need to be maximized. And it is easier said than done. There are too many parameters. Maximization of the likelihood function may not be so trivial. So you may have to come up with some clever optimization techniques. One of them is EM algorithm or stochastic EM algorithm, etc. I'm not going to go into the details. But one important thing is, in our work we have proved that necessary conditions, Lipschitz conditions that you need to show that the MLE is asymptotically normally distributed. And it will be asymptotically unbiased, consistent, and the information variance covariance matrix is the inverse of the information matrix. So, if I want to know what is the mean lifetime under normal operating conditions, all I am looking for is the expected value of y under normal stress level. Remember, the data has been collected from different stress levels. So, or even a general function of theta. Important thing is to note, it doesn't matter what the expected value of y under normal stress condition because it's a function of theta. So if I have the maximum likelihood estimate of theta, I can immediately get an estimate of expected value of y under normal stress level. And that is estimated. Usually you use a delta method, come up with an estimate, come up with a standard error, you can construct asymptotic confidence intervals, etc. So, not only that, estimation is only one part. The other part, like I said before, the Norris-Landsberg model is a general model because there are three different camps of mechanical engineers who use only their model. You can actually observe a data, you can ask which model is the most suitable one, you can do hypothesis testing. For example, if I want to know whether the Coffin-Manson-Arrhenius model is sufficient, all I have to do is test for the hypothesis A is equal to 0. If I want to know whether it is Coffin-Manson model, I have to test for A equal to 0 and the energy at A is equal to 0. So you can use Wald test, likelihood ratio test, etc. So there is a whole plethora of techniques that we know, we can inject into the analysis here. So we can further assume different members of the shape scale family. Remember, I didn't assume any particular distribution. Which distribution you use? You can pick different members of shape scale family like Gamma, Weibull, Birnbaum, Saunders, etc. You can use information based criteria like AIC, BIC to decide which one of the lifetime model is appropriate for modeling these data. So maximizing log likelihood value, AIC, BIC, all these criteria, phi divergence criteria can be used to do model selection. So one another thing is the ordinary least squares estimator, we can do best linear unbiased estimator. We know the ordinary least squares estimator assumes the error variance to be homogeneous and they are uncorrelated. But in the censoring scenario, you have to use order statistics theory. And you can develop a best linear unbiased estimator similar to OLS. But OLS is not optimal. But best linear unbiased estimator is optimal. So you have to assume the error variables epsilon ij, jth observation for the ith unit or ith stress condition has IID with some density g. It has a location parameter and a scale parameter. Then it belongs to the log location scale family. Then it has a scale parameter sigma, location parameter mu sigma. I have parameterized deliberately in that way because the location parameter will relate to the mean. I can ask how far away it is from a particular value in terms of standard deviation units. That's all. It's just a reparameterization. So log of Yij are independent and they will have log of beta I plus epsilon ij. Epsilon ij has this density. Now we can set up a mean vector variance covariance matrix. The expected value of the log is this function coming from the model that we assumed. So the expected value I denote by mu j ni. Covariances are given and between different stress levels the covariances are zero because they are independent tests. Within one stress level all the observations are correlated and because they are ordered. So I have what is called as a blocked variance covariance matrix. So note that mu j ni, sigma jk ni are all known. Once you tell me that you have a Weibull family or Gamma family, those guys are known. Either you can numerically compute or you can simulate. Either way, you can find what they are. So all you need is the data is given here, yi. What are those? Log lifetimes. So log times to break down. They will have different stress levels. So each stress level gives you Ri observations out of Ni, and N1, N2, Ni are all different. And this is my observational vector. And it has a covariance matrix, 1 over sigma squared, covariance of Yi. It's a block diagonal matrix of sigma 1, sigma 2, sigma I. So all you do is do something like Gauss-Markov theory. So you have N to be the total number of observations, create a vector 1, you have minus log f coming from Coffin-Manson model, minus log delta t, etc. I have model parameter theta. Theta has the intercept, the slope, power parameter, activation energy and standard deviation. So that's 5 parameter model. But they follow, you can derive them using Gauss-Markov theory. And you can come up with the estimates. So then with A is this, we have the expected value of y to be A theta, covariance of y to be sigma square sigma, just like least squares theory, regression model. I have an expected value which involves a matrix A that I know. Theta is the parameter that I do not know. You can find Gauss-Markov theory estimate. So all it does is it takes the
quadratic form. Y is the observed data, A theta is the expected value transpose, inverse of the variance covariance matrix sigma inverse Y minus A theta. Once I minimize this, I get the least squares estimate, which is what is called as best linear unbiased estimate. This is not only for complete sample but also for censored sample. And these least squares estimates, there is a old work of Chernoff, Gasworth and Johns. They have proved asymptotic properties for this. They have studied conditions under which the asymptotic normality holds, etc. So, asymptotic normality and the variance covariance matrix comes here, looks exactly like least squares estimate. So, only thing is everywhere you have a sigma matrix. And is this sigma matrix complicated? For example, in one of the data that we analyzed, sigma is of dimension 43 by 43. We have to invert. But that's not a problem, because the matrix sigma, if you look, is a diagonal matrix, block diagonal matrix, so the inverse is very easy. So all the inverses that you have to do are in lower dimension. So computationally, it's not challenging. And that's what I mentioned here. The expected value of Y normal under the normal operating stress or any function h of theta can be estimated. Once again, you can use the delta method to derive their variance, covariances, etc. Objective, you can now take the estimation method that we developed to convert it into a design problem. How to design? Objective is to maximize the efficiency of the estimate under a specified budget. If the manufacturing firm gives you $250,000, says that you have to conduct a test, I want you to come up with an estimate of the mean lifetime under normal stress with an accuracy measure. How to do this? This is the question. And the objective function, in this case, I can take the determinant of A transpose sigma inverse A. Remember, A transpose sigma inverse A is related to the variance of the variance covariance matrix. Once you have a variance covariance matrix, we need to come up with an objective function. We can take the trace or the determinant. So I have taken here trace, the determinant. All you have to do is now, it's a constrained optimization. You need to optimize these quantities such that the cost is less than or equal to a given budget. And that's a constrained optimization. But A itself is a block matrix. It will have A1 transpose, A2 transpose, AI transpose. Those are the matrices corresponding to the I testing environments. So the trace of A transpose sigma inverse A, because of the block diagonal form, is the sum of the traces. So we have to optimize them corresponding to just the sum, which is a simple X. So the above trace property also holds not only for the best linear unbiased estimator, but also for the maximum likelihood estimator. So use of trace is computationally simpler because I have a block diagonal matrix. But it does not account for the correlation between estimates of the model parameters for which determinant is better. But the determinant does not have this additive property. So therefore, the trace is easier computationally, but you can use either. In the case of determinant, you have to do numerical optimization in a high dimension. So now I'm going to talk about one particular type of device. It's called one-shot device. I have time?
Yeah, 8 minutes.
8 minutes, that's good. I have finished only 48 out of 86 pages. I talk a lot. This is one-shot device data. What is a one-shot device data? I did not know what this was until 2008. I had a car accident on the highway. A young girl like my daughter's age cut in front of me when I was driving home at 90 kilometers an hour. We had a head-on collision. And I had at that time a Volvo and she had a Toyota Corolla. and when we collided, the airbags in my Volvo deployed. So I just bounced on the airbag, but the young girl's car, the airbags did not function. So she was seriously injured. And the ambulance came, the two of us went to the hospital. When I was going in the ambulance, I was thinking, what kind of data this is? How does one test for the reliability of an airbag? You all buy cars, the car warranty is given, but you don't know what is the reliability of an airbag until you have an accident. And that's what is a one-shot device. A one-shot device is a device that you know is supposed to operate, but when you operate it, either it works or it fails. All you know is it is just 0-1 data. Both are censored. If it works, then you know your airbag was good for that many years. If it failed, you know it failed sometime before, but you don't observe the lifetime. So these are what are called as one-shot devices. And there is a book in Wiley, myself and two of my students, Ling and So. Exact failure time is unobservable. You only observe a binary data. What is known is only whether the device is functional at the time of the accident or not at inspection time. These are special form of data and special form of equipments that you do. So how does the data look like in this case? Think of cars being tested for the airbags. Then what you do is you test the cars at different speeds. For example, you collide on a stationary object at 10 kilometers an hour, airbag will never get employed because the speed was low. And then you increase the speed to 20 kilometers, 30 kilometers, etc. That's your environment. And at 10 kilometers, you don't crash just one dummy car, but you crash 10 of them. And then at 30 kilometers, you crash 10 of them, etc. You find only the inspection times, tested devices, how many cars that you tested, failed devices, how many devices failed. This is the form of data that you get. So our goal is to set up a likelihood function. This likelihood function is very familiar to us. It looks like a binomial likelihood function. Either the unit failed at the inspection time or the unit survived at the inspection time. It's a familiar binomial form. What do I do now? I now can put the Coffin-Manson model that I had earlier corresponding to the probability of failure. So instead of the mean, I change it to a probability using a link function, and I can analyze the one-shot device data under the Coffin-Manson model in the same way. So that's the idea. So model selection can also be performed. We can use test statistic to see whether the link functions is suitable or not. All kinds of things we can do. Advantage, the problem is that you do not observe the lifetime. All you observe is a condition. In survival analysis, this is sometimes called as current status data. In reliability theory, it's called a one-shot device data. But the inference that you develop will be robust because it's not based on the lifetime data. It's based only on the circumstance, whether it is a success or a failure. And your true parametric distribution is unclear. We can do model discrimination in this case. What is a good lifetime model to use? So recall how I connect this to one-shot device. I assumed the model, then I took yi and yj to be like in proportions in means, and they are nothing but the expected value of the lifetime under the ith stress level divided by the expected value of the lifetime under the jth stress level. I have used the model, Norris-Landsberg model. Classical proportional hazards model is not suitable in this case. The proportional hazards model, as the time progresses, the hazards have to be same proportion starting from start to end. But here it will not be because of the non-monotonicity. But this model is applicable here because we do not need monotonicity like the proportional hazards model. So that's an advantage. So using Gauss-Markov theorem, we can estimate the unknown parameter like I did before. And it can be shown that this possesses asymptotic normality, etc. So I'm going to skip certain things. There is a lot of work on optimal design, etc. But I'm going to come to the setting of the test environments. So this is a simulation study where Norris-Landsberg model is being used to the setting that I gave earlier. This is the data that Yang produced. Parameter setting is activation energy A, B, etc. are all set. And this is how the Norris-Landsberg model results show up. That I have taken different lifetime distributions because I have flexibility. I have a log normal here, Weibull here, log logistic here. I take very small sample sizes, Ni equal to 4. That means at each stress level, I can test only 4 units. The units are expensive. And I have censoring here. I have done the best linear unbiased estimate. I have done the maximum likelihood estimate. I have compared the bias and mean square error, coverage probability, etc. Shockingly, even with a sample of size 4, you can attain near nominal level for confidence intervals. And you can see that the confidence intervals are get close to 95%. But because Ni is 4, if I show the results for Ni equal to 10, you will notice that they are all close to 0.95. So now I can do model discrimination for the data that Yang produced. I ask, there 20 units were tested at each stress level, Ni equal to 20, Coffin-Manson, Arrhenius and Norris-Landsberg model, and I have produced here the model discrimination results. And what they tell you is, if truly it is a Norris-Landsberg model that produces the data, what are the chances that you accept a Coffin-Manson model by mistake? Turns out to be 0.0053. It's very, very small. If I look at here, with Ni equal to 20, I have a Norris-Landsberg model is the true model. I accept it 66% of the time, etc. So you can do model selection and model discrimination using this approach. And I have given here the trace. Remember the optimal design. Trace under different test environments. I equal to 1 and I equal to 4. Under 4 different stress levels, I have taken different test units and I have given the trace under test environments. What is interesting to see here is I have given the relative trace efficiency under test environment I equal to 1. What is the relative trace efficiency? Relative trace efficiency is ideally if I collect all the data, what will be the trace? If I terminate early, for example, out of 20 units, I terminate at 8th failure. After 8 failures, I take the ratio of the trace. I know it's less than 1. But close to 1 means that even partial data is sufficient for making inference. And that's what you see here. You see that when I take Ni equal to 1 under test environment, with 1 information, I have 1. But if I take 10 units, if I observe only 1 failure, I get only 29% of efficiency. But what is nice is you can see here, even with 5 failures out of 10 censored experiment, you get 80% of the Fisher information that you can get. So that tells you censored data is quite often very efficient. You don't have to make all the units fail. You can save some of the unfailed units and use it for other testing purposes. So when Ri by Ni goes to half, 50%, the relative efficiency is close to 80%. So 50% of failures is sufficient to capture 80% of efficiency in the inference. So you can close your eyes. I'm going to skip a few pages and go to the illustrative example and stop there. Okay. This is the data. This I'm going to take just 2 minutes. Okay. This is a recent data. The data is from one of my collaborators from Japan, Shoji, involving a test of chip scale package. They are called CSPs if you go to the market. They are solder joints under 12 thermal cycling profiles. These are the groups, 12 groups, and these are the temperatures from minus 40 to 80, minus 40 to 30, etc. Notice delta T. For the first group, delta T is 80, minus 40 is 120. So, if I come to 30, 80, which is the 8th group, delta T is 50. The difference between maximum time and the minimum time. These are the delta T. How many cycles they went through, frequency per hour, 1, 2, 3, etc. This is my F that changes for every unit. Mean life is given here, the average lifetime, mean life in hours, mean life in cycles. How many cycles they will last, how many mean life in hours. So, under each test condition, 5 CSPs were tested. If you generate a failure time data from log normal distribution, it will mimic what we observed there, exact life hours. And you can use this to make estimation. I have given here AIC, Akaike Information Criteria. Norris-Landsberg model, you could use Weibull, you could use gamma, log normal, you can even model semi-parametrically. For all of them, you can find the estimates of the parameters and you can choose which model works best for your data. All that is possible simply because of the formulation that we have created. You can estimate the reliability function. Semi-parametric model gives a good fit as the best compared to the best parametric model. So you can use a semi-parametric setup in this particular case. The same data, if the data were censored, you can do the same. You don't need a complete data. We saw that with 50% of the data, you can get 80% efficiency. So censoring allows you to stop the experiment early and you can capture enough information. And that is all. Thank you for listening, even for pretending to do so. Thank you very much.
Thank you, Professor Balakrishnan, for giving a nice, very informative talk. So, couple of questions because of lack of time, but there's a couple of questions. Of course, we know that there will be a lot of questions, and at least a couple of questions you can ask later. Discussion will be there in the lunch or tea time that you can. He will be available today evening and tomorrow. So
otherwise, you can write to me.
Yeah.
You had a question.
You are mentioning that ratio RI by NI, if it is equal to 0.5.
If it goes to.
Yeah, if it goes to 0.5, it is enough, it captures around 80%. But that RI by NI alone is sufficient, or whether that frequency also plays a role?
No. In this particular case, RI by NI is enough, because when I take the ratio of RI by NI and take expected value in the model for RI by NI, that F to the power something is common at the ith stress level. So when I test at the ith stress level, all units have Fi as the frequency. It's a multiplying factor that cancels. So the efficiency is a function purely of Ri and Ni.
Totally independent of frequency.
Right. Yeah. So at the ith frequency, whatever you fix, if you terminate at the 50th percentile or 50th order statistic, for example, then you are bound to achieve close to 80% of efficiency.
So,
yes.
Actually, all the vehicles that are brought into the market, it goes through a reliability testing, like crash testing and all.
Crash test?
Crash.
Yes.
Are any of these models used in analysis?
Actually, well, the industry will never share their data with you. But I have a good friend. It's when you are old, you develop all these friends who turn out to be good later on. Gary McDonald is a professor at Oakland University. He was the chief statistician at General Motors in Detroit. And he used to supply me some data from old reports. He cannot produce the recent data. And one of the data is actually a famous data. It's called helmet head crashing data. That was conducted in the General Motors. So some of the data that he gave me, we actually used the stress as a speed. Unfortunately, the data they record is not very nice. They just record what speed it went in. It's easy to measure. They plan it, they crash it. But it may also be a function of temperature, because sometimes the airbags get affected by humidity and temperature. So the probability of an airbag failing in Trivandrum will be very different than a probability of its failure in Toronto, because there the temperature is -30. So therefore their data is not a polished data. So we have used it as one of our illustration in our book. But more sophisticated data are available in what are called as magnetorheological experiments, where they test engine oils and different viscosity, different temperature, different pressure. So there are different settings, and the mechanical engineers are usually very good at observing all of that. So I have rich data from that experiment. So the General Motors data is not very good.
Okay, thank you very much. If there are further questions, you can discuss during lunch time. Okay? Okay.
Thank you very much.
Thank you.
Thank you.
On behalf of the organizing committee of WSTA 2026, I express our sincere gratitude to our distinguished session chair, Professor P.G. Shankaran, for graciously chairing this section and for sharing his valuable time, guidance and encouragement. I also extend our heartfelt thanks to our esteemed keynote speaker, Professor N. Balakrishnan, for delivering such an enlightening and thought-provoking keynote section. I would like to thank all the participants, faculty members, researchers, and students for your enthusiastic presence and active participation. To express our gratitude and appreciation to our speaker, Professor N. Balakrishnan, I would like to invite our session chair, P.G. Shankaran, to hand over a token of appreciation.
Already given. Already given.
No. This is different.
Thank you very much.
Also, to express our gratitude and appreciation, I now invite Professor C. Sadish Kumar to kindly come forward and present a token of appreciation to our esteemed session chair, Professor P.G. Shankaran.
Oh, that's an announcement. That's nice. It will be useful to go to the temple.
Okay, thank you.
Good afternoon, everyone. A very warm welcome to all of you to Technical Session 2, Plenary Session of the WSTA 2026, 11th International Webinar on Recent Trends in Statistical Theory and Applications. It's my great pleasure to welcome our session chair, Professor P. Mohanachandran Nair from Department of Demography, University of Kerala. Professor Mohanachandran Nair is a distinguished demographer whose academic and research contributions have significantly advanced the field of demography, population studies, public health, reproductive health, aging, migration, and actuarial science. He also guided the activities of the Population Research Center, one of the premier research centers in the country, supported by the Ministry of Health and Family Welfare, Government of India. He serves as the General Secretary of the Demography and Health Research Center and has contributed extensively to academic publications, conferences, and collaborative research in population and health sciences. We are indeed honored to have him preside over this plenary session. We are privileged to have two eminent speakers with us today. Our first speaker is Professor P.G. Shankaran from the Cochin University of Science and Technology, Kerala. Professor Shankaran is a highly respected statistician known for his
I will use my time. So don't repeat.
Our second speaker is Professor Prabal Roy Chowdhury from the Indian Statistical Institute, New Delhi. Professor Roy Chowdhury is a distinguished researcher whose work has made valuable contribution to the field of statistics. We eagerly look forward to his presentation and the insights he will share with us. With that, I now invite Professor P. Mohanachandran Nair to kindly take over the proceedings. Thank you.
Good afternoon to all. Yes, I am not taking your time. This session, two papers already mentioned, are also the speakers are very eminent and very senior. You are lucky to hear these two speakers. Professor Sankaran, all of you know, not only a statistics, head of the Department of Statistics, CUSAT, he is also the vice chancellor in charge of the CUSAT University. Okay. Then Roy Chowdhury. Okay, professor. He is also an expert and senior person. Then anyway, you are so lucky to hear these people, and you please interact with them because they are very experienced personalities. Okay, I welcome Professor P.G. Sankaran to present them.
At the outset, I thank Professor Sadish Kumar and the organizing committee for inviting me to present some of the latest work I have done with my student Miss Rilfa this year. So the title of the presentation is Additive Multiplicative Rates Model for Recurrent Event Data with the Committing Risk. When you see this title, there are many ideas. One is additive model, additive rates model, which you have familiar, those who are working in reliability and survival analysis, additive hazards model. Similarly, additive rates model in the case of recurrent event data. The second one is multiplicative rate model, which is also familiar, such as proportional hazards model is one of the popular multiplicative hazards model. So that is the multiplicative rates model. We are combining these two, additive and multiplicative rate model. Then we are considering recurrent event data, not the usual lifetime data, whether the events can be recurred. For example, recurrent hospitalization of patients or recurrent breakdown of vehicles, etc. Then other concept which I included here is committing risk, because this recurrence can happen due to several reasons. Maybe this recurrence hospitalization may be due to different diseases. So these are the another concept, that is the committing risk. So this is the roadmap of my presentation: brief introduction and literature review, followed by research gap and contribution of this particular presentation. Then we discuss model and the semi-parametric inference model I am going to consider here, and then asymptotic properties of the estimators of the model. Then conducted a simulation studies to assess the efficiency of the proposed method. Then I considered one data which you can see that, in which you can see that this model is illustrated efficiently. Then, as mentioned earlier, many outcomes in clinical and epidemiological research are recurrent events that occur repeatedly over an observation period. For example, there are repeated epileptic seizures in neurological disease patients, or recurrent hospitalizations in disease patients, repeated exacerbations and chronic obstructive pulmonary disease patients, etc. These are some of the examples. Then, when you consider recurrent event data, there are two time scales one can use. One is the total time in which you can measure the number of recurrences occurred during that time. That is the total time you can do. The second one is the gap time. That is the clock reset to zero after each event occurred, so that the time measures the duration between two successive events. That is the gap time. The gap time is appropriate when recurrence risk depends on the time elapsed since the most recent event, example infection recurrences. Then choice between the total time and gap time has important implications for model interpretation, estimation and handling of covariates. Then coming to this committing risk. That committing risk arises when a subject is at risk of k distinct mutually exclusive event types, such that occurrence of one type or one cause precludes or alerts the risk of the others at that instant. In that case, what we observe when you consider the total time, NIJT for subject I and J types, that is denote the cumulative number of events experienced up to time t due to cause j or due to type j, that is Nij star t. Since the k causes are mutually exclusive, each realized event belonging to exactly one cause j, and the cause specific processes Nij star t, that is Ni1 star t, Ni2 star t, etc., Nij star t, jointly decomposes the total recurrent event process for subject I. For example, if you have k committing risk, j equal to 1, recurrences attributable to cause 1 or type 1, j equal to 2, recurrence attributable to type 2, and j equal to 3, the recurrence attributable to type 3. Examples are committing causes or committing risk. Then for subject I, if there are n subjects, for subject I, let the Nij star t denote the cumulative count of type j events experienced up to time t in the absence of censoring. Then the expected cumulative number of type j up to time t is given the covariate history. Suppose the patient's history is known, for example, gender or the other history, patient's history, cholesterol level, or some other history levels are also known, age, etc. Then we have the cause specific mean function, that is the expected value of Nij star t given the covariance history equal to mu ijt given uit. So this expected value of Nij basically is of interest. That is the cumulative mean function, expected cumulative mean function, that is the expected Nij star t. So this mu ijt is the cause specific cumulative mean function of Nij star t. This is the interest. Now what literature do is you assume certain models for this mu ij t given uit. That is the usual thing. For example, another concept which is closely related to this mean function is the rate function, that is the expected value of d Nij star t given uit, that is usually denoted by lambda ij t given uit. This lambda ij t is the cause specific rate functions. Then what we do is, one approach is this mu ijt or lambda ijt, that is the rate function given the covariate. We assume that these covariates, this model, the particular model, have the specific form, that is the additive model, that is mu ijt given uit is equal to lambda ijt given uit is equal to lambda naught t plus eta j uit, where eta j is actually the regression coefficient. This is known as additive risk model. uit is the set of covariate that may be time dependent covariate. Then this mu lambda naught j t, that is the baseline cause specific intensity function or risk function. That is the lambda naught JT. If you assume some particular distribution for lambda naught JT, you can have parametric model, but if you are taking not assuming any model, for example, if you are not assuming exponential model or regression model, then you will have completely non-parametric setup where your objective is to estimate this lambda naught JT, overall lambda naught JT, which will be a non-parametric quantity, and this parameter regression parameter. The second model is a multiplicative model which is closely related to this proportional hazards model that will have this form which you are very much familiar. This is a proportional hazard model. Then I'm going to review a few papers was started from 1981, that is Prentice, Williams and Peterson. They started the analysis of such multivariate failure time data via marginal distribution, then followed by Anderson and Gill extended the coarse proportional hazards model to counting process under a multiplicative intensity framework. Then there are other papers, then Cook and Lawless, they introduced a robust rate-based method for the recurrent events with no distributional assumptions. Then Lawless and Knight proposed a simple robust method for the analysis of recurrent events. There is a book by Lawless also, Lawless and Cook, for a statistical analysis of recurrent event data. That's also there. Then there are other papers. These are the, and we have considered, myself and my student Anisha, we have published 4 or 5 papers on recurrent event data using gap times, not total time, using gap times. Myself, Sridevi and Ashlyn, we have published a paper on cost-specific rate functions for pan count data with multiple modes of recurrences. This is appeared in Journal of Applied Statistics. Then myself and Sisuma, we developed a non-parametric inference proposal for recurrent event data under competing risk. And there are other papers. Recently, myself and Hari published 3 papers on recurrent event data under different setup. Then the research gap is the following. That is the simultaneous modeling of additive and multiplicative covariate effect in the presence of competing risk for recurrent event data has received limited attention. Standard recurrent event method require further adaptation to yield valid inference when one event type can preclude or alter the risk of other. Then the simultaneous modeling is the gap which we found during our literature study. Then our contribution is to propose the following, that is to propose an additive multiplicative rate model for recurrent event data with the competing risk. Then coming to model, we have n subjects, that means n patients, for example n patients. Then we monitored these patients over a follow-up period, and there are k competing risks, that is j equal to 1, 2, 3, etc. k. Each subject is at risk of multiple mutually exclusive event types. The occurrence of one type precludes or alters the risk of others. Then, as mentioned earlier, Nij star t is the cumulative count of type J events for subject I up to time t. Then UIT, that is a set of covariate, that is ZIT and XIT. There are a set of covariate, possibly time dependent, and ZIT, why we classify or partition into 2 covariates, the reason will be the following, that is we have additive model and multiplicative model. The same covariate may not be appropriate for both the model. So we considered 2 different set of covariate. Same covariate can also be the part of the both model, but it is not necessary in practice. So we consider ZIT and XIT separately. Then the conditional mean increment of the cost-specific counting process, that is expectation of DNA-JT, that is the which we have discussed earlier, that is lambda IJT. Then we consider the model. The lambda ijt given UIT is G1 of eta j zit plus G2 of beta j xit into lambda naught ijt. Where what we can see that these G1 and G2 are two functions, two non-increasing continuous functions, and then eta j and beta j, they are the regression coefficients. For example, when eta j is equal to 0, then what will happen? It will reduce us to the multiplicative model, and if beta j equal to 0, you can reduce us to the additive model. That's what we have done. Then we can take different g functions. For example, g1 equal to g1 of x equal to x, or g1 of x equal to log x, or g1 of x equal to e to the power of beta x, which will provide different types of model, including Cox proportional hazard type models, or combined with additive model, or proportional odds model combined with additive model, etc. Those things you can get. Then additive component G1 captures the direct absolute contribution of the covariate, while G2 modulates the baseline through a relative scaling mechanisms, which I have already. If G1 equal to G1 of x equal to x and G2 of x equal to e to the power of x, it will be actually a proportional hazards model combined with an additive factor. That is then our objective is to estimate this eta j and beta j plus this lambda naught j. That is that. Okay, this that's the general model. That's next to both the special cases, and directly extend the additive multiplicative hazards model of Lin and Wing to the recurrent event committing this setup. Okay. Then this model is very flexible when different subsets of covariate are hypothesized to act through distinct mechanism on each committing causes. That to make the inference, as mentioned by Professor Balakrishnan, this is censoring is inevitable in survival analysis and reliability theory. We have a censoring time. Then we assumed that this expected value of dnij star t given UIT and censoring time is independent of that censoring time. That is the usual assume. Then observed cause specific given nijt is this is the observed number of events up to time t due to cause j. That is observed one, which means that some of the patients will be censored. So that will carry out this minimum of t comma ci. That is observed one. Then this is the parameter tau j is eta j beta j prime, denote the true cause specific parameter vector. Our objective is to estimate that tau j and beta j. Then to felicitate estimation of tau j, we use counting process approach. For that, we construct a martingale. Then how to construct a martingale? We consider Nijt comma tau j, that is equal to Nijt. Oh, sorry. This is maybe. Mijt is Nijt minus this quantity, which we usually use in estimation of baseline hazard function. You can refer counting process approaches in survival analysis, Fleming and Harrington book, all those books, or Anderson and Gill book. These are the construction of martingale. Then expected value of dMijt, that will be 0. That is idea. Average expectation of that will be 0. That is that. So that you can use expectation of dMijt equal to 0. That will yield the estimation of this baseline hazard function and beta j and eta j. Then under computing this framework, this will give to a estimating a function that is uj tau j j equal to 1, 2, 3, etc. K. Then you can reparameterize it and you will get this as estimate of this. This will be, this is the estimate of the mean function, mu naught j hat t, that can be estimated these two. Okay, then you can estimate tau j. Tau j is beta j and eta j. You can estimate these two quantities by constructing the estimating equation or plugging the estimate of mu naught j t. Then you will get this uj to tau j. Then equating uj tau j equal to 0, you will get the estimate of this quantity. Some modification is required. Then the estimate of tau j hat for each j is obtained by solving uj tau j equal to 0 independently for each pose. Then this is possible because of the estimating functions across different causes share the same covariance process but involve distinct parameter covariance and counting process. Then this considerably simplifies both computations and asymptotic analysis. Then I'm not discussing much on this asymptotic properties of these estimators. For that, we use Martingale central limit theorem. Basically, we use Martingale central limit theorem to prove that we need some regularity conditions C1, C2, C3, C4, C5, C6. These are the regularity conditions, and then these conditions are standard smoothness and boundness requirements, and they satisfied by choosing L no greater than the maximum observed follow-up time across subject. Then condition C5 is an identifiability requirement. Then the weight process Qj, little qj bar is well defined under C2 and C6, etc. Then basically these are the asymptotic properties. This tau j hat minus tau j, root n into tau j hat minus tau j is 0, 0 mean multivariate normal distribution with a variance covariance matrix this, then which can be estimated analytically, but it's very difficult, but you can use bootstrap method to estimate that one. Then you can prove the consistency theorem. Then you can also prove the asymptotic this one. I am not this next mu naught j hat t minus mu naught j t, that will converge almost surely to 0. That is almost sure consistency. That is almost sure consistency. That is there. Then you can also prove the Gaussian process for mu naught j t. Then the simulation study. Event times are generated from a non-homogeneous post-solve process with a post-specific rate function following the multiplicative additive structure with gx equal to x and g1x equal to x and g2x, not h and g. G2x equal to e to the power of x and Weibull type baseline hazard rate. So the base hazard rate, they are the Weibull type hazard rate, baseline hazard rate. Then we consider the Cox proportional hazards model, that is G1 x equal to e to the power of x and G2x equal to x. Then the model is like this. Then we generated this covariate xi from uniform distribution and zi from Bernoulli distribution. We generate censoring time again from uniform distribution, and finally we got this bias and MSE and ESD, that is estimated standard deviation, that is the coverage probability for different sample sizes. Bias is very low. You can see that it is very low. When you have 500 sample sizes, it's very, very low. And eta j, it's almost 0. Then lambda, beta j hat, etc. These are the things, two parameter value. Then bias is negligibly even at n equal to 100 and decreases monotonically towards 0 as n increases to 500. ESD decreases at the rate of n raised to minus half for all causes. This is route and consistency is established. MSC decreases monotonically with increasing sample sizes. Coverage probability of the nominal 95% confidence interval approaches the target value, that is 0.95. Then for beta j hat, that is the regression parameter, EST and MSC are consistently larger than for eta j hat additive model, reflecting the greater curvature of the nonlinear link. This pattern is most pronounced for cos 1 and the least pronounced for cos 2. Across all three causes, bias, MSC and EST and coverage probabilities are stable and comparable. These findings provide strong empirical support for the theoretical asymptotic results and demonstrative the practical adequacy of the model. Then we consider data, that is bladder cancer data. This is from a randomized clinical trial conducted by this particular research group, reported in Bayer 1980 and subsequently analyzed by B. Lin and Wiesfeld in 1989. Then patients with superficial bladder tumors surgically removed prior to randomization were allotted to three groups at placebo, thiotropia and pyridoxine arms. Newly developed tumors were excised at each scheduled follow-up time. The data set is available in our package. Then analysis is restricted to two groups, placebo and thiotropia groups, treated as two competing types of tumor recurrences. Then placebo group, there are n subjects, n equal to 49 subjects, 19 event-free, 61 total recurrences. The second group, 38 subjects, 20 event-free, 23 recurrences. Total n equal to 87. Observation period spans from 0 to 59 months. Then two baseline covariates, one is ZI, number of initial tumors at study entry, then XI, that is diameter of the largest tumor. Then this is the snapshot of this data, that is patient with the initial tumors, largest tumor and follow-up time. Then ZI, that is the number of initial tumors, that is the additive covariate, and XI, that is the diameter of largest tumor, that is the multiplicative covariate that we consider. This is that. Then objective is to assess how the two baseline characteristics jointly influence the cause-specific rate of tumor recurrences. We considered the model which we have discussed earlier. Then we estimated this eta j and beta j. And then there are two quantities, eta 1, beta 1, eta 2, beta 2. These values, estimated values are there. And you can see that eta 1, eta 2, that values are small, but beta 1, beta 2, these estimates are relatively significant, very high. Then for the placebo group, eta 1 hat is 0.0485, greater than 0, indicate a positive absolute contribution of initial tumor count to the recurrence rate. Each additional initial tumor is associated with a direct elevation in the rate of recurrence under placebo. Although the 95% confidence interval for eta 1 hat includes 0, the positive direction is consistent with the prognostic role of baseline tumor burden. Beta 1 hat is 0.7263 is positive, suggesting that larger tumor diameter amplifies the baseline recurrence rate. Then for the thiotropia group, the eta 2 hat is very small, 0.006. It is substantially smaller than the placebo counterpart. The absolute influence of initial tumor count is markedly attenuated under thiopita. And beta 2 hat is minus 0.54 is negative, suggesting that larger tumor diameter is associated with a reduction in the relative recurrence rate under the particular type. Then the 95% confidence interval marginally includes this 0. This negative multiplicative effect under this particular covariate with the positive effect observed under placebo. Yeah, I am completing. The reversed multiplicative rate may reflect their differential treatment response. Okay, so basically the proposed additive multiplicative framework enables this nuanced characterization of treatment specific covariate effect. Then we also plot the mean function, that is the mean function. The placebo rate is substantially higher than the Toyota rate throughout the 59-month follow-up. So then, in short, we proposed an additive multiplicative rate model for recurrent event data with competing rares, accommodating both additive and multiplicative covariate effect. Cost-specific estimating cost-specific rate functions are constructed separately for each competing risk using a martingale-based approach with baseline mean function recovered non-parametrically. RAR sample properties of the proposed estimators were established. Simulation studies confirm negligible bias and low MSE. And application to bladder cancer recurrence data reveals that the placebo and Theotapa groups exhibit markedly different additive and multiplicative covariate effect. And then future work, extension of the present work to incorporate frailty terms for handling unobserved heterogeneity among subjects is an area to be explored. Development of Bayesian inference procedure for the proposed model is an area to be studied, but we already studied this one. Second thing, we already completed that work, Bayesian inference. Then that's all. These are some of the references. Lot of.
Okay, thank you. Last after the second.
No, just because I may leave. Because I just
okay, then one or two questions.
best way.
If anyone has
Any questions? Any suggestions?
Sir, when you go for the simulation structure, you have selected certain specific values for beta and eta. So, is there any logic behind selecting those particular values?
No. We have considered. I presented only few slides only. We have considered different combinations for eta and beta. We considered three causes. So basically three causes corresponding to three causes, three beta 1, beta 2, beta 3, eta 1, eta 2, eta 3. We presented these 6 values for one set of combination only. I guess we have in the paper when we send for publication, we consider 3-4 combination, and I have considered variable type. Instead of variable type, you can consider robots or other models also we can use that.
It's a question of how you select those parameters, the model itself.
No. Select parameter, what we do is the proportional hazards model, we consider the positive impact and negative impact. Beta, we usually consider one positive and maybe value which is slightly higher than 1, that is 1.5, etc. And even smaller value for 0.5 or 0.2. Even for negative value also we consider minus 1.2 or something like that. That's all. That's no particular logic behind that. That the odds ratio, basically in the proportions that the odds ratio is 1, that will they are equally, because that is parallel, that those two curves will be parallel, proportional for different individuals will be parallel. That's the idea, the proportionals are. Thank you. Okay.
Thank you.
I now invite Professor Mohanachandran Nair to kindly come forward and present a token of gratitude to Professor P.G. Shankaran.
Okay, thank you. I don't know. Elaborate job. ഞാൻ പോയി കഴിഞ്ഞാഴ്ച ഒന്ന് പോയി
You are having after lunch or now?
Not now, maybe 1:30 I will have lunch, then 1:45 I will go.
Yes, yes.
Yeah.
Slide.
Here. He's here. He has changed it.
Prabha, I think you have to speak it. But I'm trying to open my slide. Okay. Otherwise, online people will not.
Sunday is there.
Sunday is the present secretary.
Yes. Yeah, actually, Shankaran was telling that he has suggested to Shinda to invite me for the ISPS, but I cannot go. It's on 21, 22, 23. I have to go back. I have a father-in-law who is 95, so we don't miss the Christmas with him. And my children come.
That is why I have taken barely.
Correct. That's why I can't go to the IASA conference in Benares.
After December.
Yeah, it's Christmas. Yeah.
In December,
I think my plan is to come to Cochin, but before that nothing, because I teach till the 10th, December 10th. So then the exam. So I have asked the registrar's office to fix the exam before the 13th, so I can leave on the 13th, and then I keep all the exams in my office. So this workshop is on the 16th to 18th. So I will leave on the 13th and come to Cochin on the 15th. Then attend 16th, 17th, but I cannot stay for the 18th. I have to go back. Now my flight got cancelled. So I have to arrange some other way, if possible. What happened?
I tried to upload my slides.
Oh, yeah.
Last December,
His visa didn't come through. Yeah, he told me. He came to the conference that was organized by my students for myself in China. They had a conference for my 70th birthday, and he told me that he couldn't go.
Yes, we change it to the remote. And
yeah, it works.
Okay, thank you. Thank you all for patiently waiting.
I don't know.
Okay, should I start? Yeah.
This is a topic about, let me first start by clarifying that
This is a paper on actual and applied game theory. So slightly orthogonal to the standard statistical analysis. So what is this problem about? It's something called hold up when the technology has a completion point. So let me first explain what we mean by this thing called hold up. This is actually one of the foundational problems within economics. If you count maybe 4 or 5 problems which are absolutely foundational to economics, hold up would be one of them. So let me give a very simplified exposition of what the fundamental problem is. So let's think of a situation where there is a supplier who is interacting with a manufacturer. So what can the supplier do? He can invest $100 so as to build a machine capable of producing a part But that is unique to that particular specific manufacturer. It's not useful to anyone else. Okay. Now let's look at the timeline of this issue. So first, suppose that the supplier actually spends this $100 and actually builds this machine. So at this point, what has happened? He has already spent the money. Now he goes to the manufacturer, and then he said, "Look, there is this machine that is extremely useful for you. So why don't you buy it from me?" But what does the manufacturer think? So manufacturer knows that the machine that has been built, that is very specific to his own factory. Therefore, it cannot be used anywhere else. So that is going to give the manufacturer a lot of bargaining power. Right? So the manufacturer realizes that the supplier is effectively locked in. Then because the supplier is locked in that case, the hold-up problem is going to arise. In the sense that the manufacturer offers to pay only say maybe $50, $40, $60 for the thing. Because he knows that if he walks out, in that case the supplier cannot sell it to anyone else. Therefore now if you look back to the start of the problem, what is going to happen? The supplier knows that if I spend this $100, I'm only going to recoup maybe $60. So that is a loss for me. Therefore why should I make the investment at all? Right? Therefore, given that that is going to happen, so this investment is not going to take place. Therefore, something that is extremely useful for the supplier, that is extremely useful to the manufacturer, as well as to the consumers, if that product was actually developed, even that is not going to get paid. Right? So, this is a significant loss to the economy. Okay, so, that is the fundamental hold-up problem which is going to lead to this, what we call this inefficiency in economy. So just to convince you that this is a foundational issue within economy, so let me just present some of the foundational papers here. So it has contributed to this field called internal organizations of firms. So for example, let us think of a multinational company. So should these companies be organized according to the countries of operation or maybe according to their function? Things like that. So how many CEOs should be there, how many people should be working under them, and so on and so forth. And there's the issue of vertical integration. Suppose there are two firms, should they be vertically integrated or not? Issue of financial contracting, international trade, and also this problem of this global value chains and so on and so forth. Right? So what are these numbers within brackets? So those are the number of citations that these papers have accumulated over time. So Klein has accumulated more than 30,000 citations. Williamson has accumulated more than 25,000 in one of his papers and more than 20,000 for another one of his papers. Grossman and Hart has a citation more than 35,000 and so on and so forth. And so it's not very surprising that Williamson has already gotten the Nobel for his work. Also not very surprising that Grossman has already gotten the Nobel. So possibly this group of workers, they are also going to get the Nobel one. Right? So it's an absolutely foundational problem. Now what we plan to do is something different from this literature, but is very much related. In the sense that all this literature that I presented you, that treats the hold-up problem from a static viewpoint. So it's a one-shot problem, and then they assume that there is a fundamental inefficiency problem there. Okay? So all of those papers were assuming this problem as given, and given that the problem is there, what can you do about it? Okay, so that was the older literature. Okay, however, the modern literature challenges these viewpoints, and the fundamental argument is that if instead of modeling it as a static problem, if you model it as a dynamic problem, where there is a dynamic, where the investment is going on over time, the people are bargaining over time, there is transfers going on over time. If you allow for all these dynamic elements, in that case we can get an outcome which is asymptotically efficient. Okay. So one of the foundational papers is this paper by this group Che and Sakovic, which appeared in Econometrica 2004. And also we have got another paper which is coming out in September in the Journal of Economic Theory. So now the basic technical problem is the following. So if you want to address this particular problem, in that case the only sensible game form is to have a game which goes on forever. That is an infinite horizon dynamic game. Okay. However, as soon as you take an infinite horizon dynamic game, the solution is very problematic, Because if it was a finite horizon game, you could start from the last period, solve the game, fold it back, and then solve for that, and fold back the solution, and so on and so forth. But if it's an infinite horizon game, in that case, doing, those kind of things are very difficult. This is a fundamentally an extremely hard problem to solve. And let me skip from the, so I'll just talk about the literature gap a bit because time is short. So what is our relation to these two papers? To extend the Che and Sakovich paper by allowing for asymmetry in bargaining power. So what Che and Sakovich did was they took an infinite horizon game and they said that suppose that the bargaining power between these two agents are not very different. There could be a little bit of asymmetry, but they're fundamentally symmetrical. In that scenario, what they argued was that the hold-up problem goes away in the sense that there is one equilibrium which is asymptotically efficient. Okay, whereas in a recent paper, Roy Chaudhary and Sengupta, what we did was we analyzed a scenario where the bargaining power is fundamentally asymmetric. One of the agents have a lot of bargaining power, but the bargaining power of the other agent is relatively small. Okay, therefore we deviate from both of these papers by considering what we call a technology with a completion point. So before I give you the formulation, so what do we mean by that? So the most useful example to think of a scenario is why say we are building a road in between say a couple of cities. Now the point is that, so maybe the cities are 100 miles apart, so even if 99 miles of the road is complete, it's still completely useless. So the road only becomes useful, only is completed for every single feet of the road connecting these two people. Right? So the net return from that project is going to be zero until the project is fully complete. Okay, so that means that there is a completion point beyond which the project immediately becomes valuable, but prior to that, the project is absolutely zero. Okay, so that is the fundamental class of problem. Similarly, if you think of some kind of R&D going on over a particular disease, again there might be academic knowledge accruing, there may be R&D going on, science may be progressing, but if you only consider it from the point of view of the development of a cure, so the mega return comes only after a cure is developed. I mean, all of us have been hoping that there is going to be this miracle cures for cancer, and people keep on telling us that the technology is developing, one of these is going to come, but it never comes, right? So it's a bit like that. So the simplest way to formulate that is to consider a surplus function, call it phi bs, where the surplus is some positive number b if the aggregate investment by these two agents exceeds some number. Here we just normalize it to 1. Whereas if the aggregate investment is less than 1, in that case the project is completely valueless. Okay? So it's essentially some kind of step function. It's 0 till this point, then it jumps up, and then it remains at that level. Okay? So that is the class of technologies that we are going to consider. Okay, again, just to convince you that this is an important class of problem to look at, let me just talk a bit about this empirical application regarding this collaboration between Apple and this Taiwan semiconductor manufacturing company. It is one of the premier companies in the world as far as this building of chips are considered. Right? So what was this collaboration about? This was the development of this advanced semiconductor chips. So these chips were, so the thickness were actually of these were 2 nanometer development. And then these chips were meant to be used in one of the Apple iPhones. Right? So it's absolutely central to Apple's development. Okay. So if you think of this problem, this is naturally a problem where the technology has a completion point because the iPhone sells in thousands and even close to maybe millions. Therefore, unless you are capable of producing actually a lot of chips at the same time, it is not very useful to have. And so the technology naturally has a completion point. And also there is an asymmetric bargaining power. So why there is an asymmetry in bargaining power? So that is because Apple is the largest single customer of this TSMC. TSMC itself is a really giant company. But even then, Apple is even more significant to this TSMC compared to anyone. And if you just talk in terms of money, this is a deal that was worth tens of billions of dollars, not millions of dollars, not even $1 billion. It was worth tens of billions of dollars, right? So we're talking about problems which are really important. And then we can give other examples, but let me know. Okay, so let me just quickly run you through the formal modeling. So we consider an infinite horizon, discrete time game between a risk-neutral buyer and a seller. So I suppose all of you know that risk-neutral essentially means that the utility functions are linear. So there is no concavity in the utility function. And then there is a cumulative investment. So BT, so is the cumulative investments at period T that consists of the investment in period 1 plus period 2 plus period 3 and so on. So you can build in some kind of depreciation, but it's not very central to our paper, so we have not done that. And this technology has what we call the completion point. And the other important factor is that the seller's marginal cost is 1, whereas the marginal cost of the buyer is greater than 1, so we just call it a number beta. So which means that the efficient thing is that the production should be carried out by the seller and not by the buyer. And there is this common discount factor. So discount factors are things that we use when you analyze any kind of dynamic games. Right? And then the game structure goes as follows. So there is, as we said, an infinite horizon, and if we pick up any arbitrary period, say t, there are going to be 3 sub-stages within every period. So in stage 1, there is a transfer stage where the buyer decides on a monetary transfer to the seller. And there is going to be an investment stage where the agents simultaneously choose how much they want to invest. They can invest 0 if they want, so that is allowed for. And there is what we call the random protocol bargaining. So nature selects a proposer randomly. So whoever nature selects as the proposer, that particular person gets to make an offer. The other person just says yes or no. If he says no, then the game goes on to the next period. If he says yes, that is the end of the game. Right? So that is the game. And we are going to solve for the subgame perfect Nash equilibrium of this game. Okay, so here the fundamental question is the following. So firstly the question of efficiency. So what outcomes are desirable, or alternatively we can say maximize the size of the cake. So the efficient outcome is that the seller makes an investment of 1 because the seller is relatively more efficient. So the production should ideally be carried out by the seller because he can do it more cheap. So the buyer should not be making any investment. And we also need an agreement should be reached in the first period itself. Why in the first period? Because suppose an agreement is reached, but it occurs 10 million years from now. That is not a very useful agreement to have. Right? So the most efficient outcome is that this should happen. Okay. However, implementing the efficient outcome is not possible. So what we are going to look for is what we call asymptotic efficiency. So suppose that the delta goes to 1, which essentially means that suppose that the agents are becoming more and more patient. So they care more about the future. In that case, the cumulative seller investment will again equal 1, the buyer investment will again equal 0, and the aggregate payoff would be within epsilon of the efficient net surplus nu minus 1. Okay. So we cannot hit the absolute efficient point, but we can approach it asymptotically. So that is what we are going to look for. So then the question is, can a desirable outcome arise as a subgame perfect Nash equilibrium? So this is the idea. Can that happen if the players are interacting among themselves? Okay, so again we are looking at a scenario where the bargaining powers are very asymmetric, and we formalize that through this assumption called this weak individual rationality or WIR that is going to fail. It fails in a very specific formal sense. So 1 minus alpha times V, that is the expected gross payoff that the seller is going to get once the project is completed. And what is minus 1? So that is the cost of making the investment to the seller. Right? So this is the gross return, this is the cost, so the difference is the profit. So start with a scenario where actually this profit is negative. We start with a scenario where the seller doesn't really want to invest unless we can find out a clever mechanism whereby he can be reimbursed. So in that scenario, what can be done? Okay, so we define something called S bar, where S bar is, this is some number, I'll just come quick later. And we start with two preliminary results. So the first result is what is called continuation efficiency. This essentially says that suppose that a lot of investment has already been done, such that the seller, even if he completes the project now, is not going to make a loss. In that scenario, what we can show is that there is a continuation equilibrium where the efficient outcome can be reached. Okay. And there is something called a punishment phase. So because our equilibrium will be constructed as follows. So the seller invests something, the buyer makes a compensation, then the seller again makes a bit of investment, then the buyer again makes a bit of compensation, and so on and so forth. But now suppose there is a phase where the buyer does not actually make the compensation, does not make the transfer. What is going to happen? Then we say that there is an equilibrium where the buyer makes the whole of the investment herself and completes the project. So that is a bad thing for the buyer to happen, because the cost of completing the investment is actually large for the buyer, because his marginal cost of doing that is high. Okay. So using these two preliminary lemmas, we can sustain what are the two fundamental results here. So the first result is that if say the buyer's cost beta, the buyer's cost of doing the production is really large, in that case the efficient vector 0, 1 can be implemented in exactly 2 periods. So it's not 1 period, it's not immediate, but it's a relatively short period. So what happens here? So in period 1, the seller invests a certain amount. Then in period 2, the buyer makes a transfer such that the seller is exactly compensated for that investment. After that, the seller makes the remaining investment, and the game is negotiated. The surplus is negotiated. And there is immediate agreement which is going to be reached in period 2. So what are the intuitions? So let me just quickly explain that. So the first thing is that once investment of this S bar is made, then the continuation game is what we defined earlier, WIR compatible. Okay. So that means our earlier lemma 1 is going to apply, and which means that now we can immediately complete the game. Now why does the rest of the strategies work? So if the buyer fails to invest, in that case the lemma 2 comes into play. Fails to invest, if the buyer fails to make the transfer. In that case the buyer is going to be punished. So the buyer because he is afraid of the punishment, he actually makes the transfer. And similarly, the seller has an incentive to actually invest S bar. Why? Because suppose he invests more than S bar. Even in that case, the transfer he is going to get is remain the same. Therefore, he is just going to make a loss. His transfer doesn't go up. Okay. However, what happens if the seller invests less than this S bar which the seller is supposed to do? In that case, you can construct an outcome such that the agreement is not reached immediately. And the expectation is that actually in the next period, the game is going to return to its equilibrium point. So that means that all you are doing by under investing is actually delaying the outcome by 1 period. And apart from that, nothing else is happening. So which is costly to you, because the cake is going to be realized 1 period later. Okay, therefore, none of these people have an incentive to actually deviate. And the second result talks of this thing called gradualism. Now suppose that the buyer is more efficient, in the sense the beta is low. In that case, the implementation requires more than 2 periods. So what happens? So here you can show that there is a sequence of investment and transfer, so that the seller makes a little bit of investment, then the buyer makes a little bit of transfer, then the seller again makes a little bit of investment, the buyer again makes a little bit of transfer. Therefore, this thing continues until the aggregate investment hits this particular level S bar. Okay. Therefore, once that particular level is hit, after that we can apply some of our earlier results to ensure that our equilibrium is attained. Okay, so the interesting question is that why can't we implement the outcome that we did in the first proposition? Why can't the seller make this full investment of S bar immediately? Now the problem is that if the seller invests too much at once, then what the buyer can do is that the buyer can make the remaining investment himself. He says that I am not going to pay you anything, let me complete the project myself, and after that let us bargain over it. And that is going to be a profitable thing because the seller has already made a lot of investment. Therefore, in this particular scenario, because the buyer's cost of making the investment is small, the earlier equilibrium cannot be sustained. And okay, so those two are the first major result, and there are some you can say something about what does this sequence of investment that the seller makes is going to look like. We can show that this is a decreasing sequence. So S1 is better than S2 and so on and so forth. Okay. And then but the most important result is this thing called asymptotic efficiency. So note that what these earlier propositions 1 and 2 says is that we can reach an equilibrium within a finite number of periods. But it's still conceptually possible that if the discount factor becomes large, as the people become very patient, actually the agreement keeps on getting pushed further and further. And as I said, suppose there is an agreement, but it's 10 million years from now. That is completely useless to anyone, right? Therefore, we need this final result which says that, so this equilibrium, both the propositions are asymptotically efficient in the sense that the delay cost still approach zero as the agent becomes sufficiently patient. Or the cost or the timing of the agreement, that is going to be a bounded one. So it's not going to blow up. Therefore, that requires a separate argument. And another nice property of this equilibrium is that, so what we are doing is saying, okay, so give me a delta, I can write down an equilibrium, but the efficient outcome is attained, say maybe within 15 periods. Now then the question can be, can you do it in a shorter number of periods? We show that no, you cannot. Okay? If in some sense this is the nicest possible equilibrium that we can hope to construct. And you can do some comparative statics, so maybe you can do some empirically testable propositions using this comparative statics, but I don't want to take up your time. And then the final thing is that we have some robustness analysis. So for example, so the technology we have been using is this step function, right? So flat and jumps up, then flat again. Now one natural question could be, suppose it increases slowly up to a point, then it jumps up, and then maybe it becomes flat. Do the results hold? We argue that yes, the results do hold. Therefore, our technology is much more robust than the one that we are working with. And also, if you look at the timing of the game, we have a game where there is there is transfer followed by investment and then the negotiation. So if you flip the game order, would anything change? So we argue that no, it does not. So again, the same equilibrium can be sustained. There will be minor differences, but qualitatively nothing changes. So just to summarize, so what we argue here is that dynamic bargaining coupled with transfer can restore asymptotic efficiency even when the technologies have sharp non-convexity. So in economics, almost always works with technologies that are convex, and the fundamental assumption is that if the technology is non-convex, hitting an efficient point is very, very difficult. Here we are working with a non-convex technology. Despite that, we can show that we can actually attain an outcome which is asymptotically efficient. And then the way that is worked, as you argue, so it works by this gradualism thing where the investment is done over a slow sequence of periods. And this has got empirical relevance because many of the modern complex R&D partnerships, for example, the one between Apple and TSMC that we talked about, that is based on exactly this kind of milestone-based stage financing. Once you develop something, there's some money given. Then you develop the next stage, again there is some money given, and so on and so forth. And finally, some questions for future research. So one property of this equilibrium is that this is not Markov perfect because it depends on the history of the game. So one question is that can you attain efficiency using strategies that are Markov perfect? So that is maybe something that we are going to work on in the future. Okay. Thank you. Any questions?
now the time for question answer.
Can you explain what is Markov here? That means it's optimal only based on the current
Yes.
immediate past.
Yeah, so the Markov strategies, so in this context of this game, Markov would say that so the strategies do not depend on what is the investment vector by the buyers and the seller. It would also not depend on whether you are in period, say, 10 or period 1000. So it should not depend on those things. But here our strategies do actually depend on what is happening along, so it is history dependent.
It is history dependent.
It's history dependent. So one question is that can you do the same thing but using strategies that are not history dependent? So as to the answer we don't.
Thank you.
I now invite Professor Mohanachandran Nair to kindly come forward and present a token of gratitude to Professor Prabal Roy Chowdhury.
Yes. We are going to wind up this session. Two presentations. The presenters are the senior persons. Then, okay, they have presented nicely and explanatory. I express our sincere thanks on all of you, on behalf of all of you, to these two speakers, Professor Shankaran and Professor Roy Chowdhury. Okay, thank you all for your patience to hear this talk.
On behalf of organization.
Just a second. Yes. She has an announcement to make.
Yes.
On behalf of Organizing Committee of WSTA 2026, I extend my sincere thanks to our esteemed session chair, Professor P. Mohanachandran Nair, for his excellent guidance and for conducting the plenary session with great distinction. I express my heartfelt gratitude to our distinguished speaker, Professor P.G. Shankaran and Professor Prabal Roy Chowdhury, for sharing their valuable knowledge, expertise and research insight through their enlightening presentation. I now invite Professor C. Satish Kumar to present a token of gratitude to esteemed session chair, Professor P. Mohanachandran Nair. Thank you.
So today's morning session is coming to an end and it's time to break for lunch. Just before breaking for lunch, I'd like to I'd like to bring to your notice some of the awards and competitions that we normally conduct in association with WSTA as well as the ICSTC, the conference that will be conducted during December. Most of these awards are sponsored by many great statisticians within our state, within the country as well as outside. So I'll just declare some of the most prominent awards. The first one that is being actually conducted right now is the Professor Kalyanaraman Sir Best Project Presentation Award. The entries, it's still open, so if some of you are willing to send your entries for the Project Presentation Award, you are still welcome. Then we have the Professor A. M. Mathai Best PhD Thesis Award. This is given in 3 subjects, in statistics, mathematics and physics. The final decision and the award declaration will be done during ICSTC. So if any of the participants online or offline would like to participate, I request you to send in your entries. We have many other awards, especially the Professor U.S. Nair Endowment Lecture Award, which is sponsored by Professor Kalyanaraman Sir. And we have the Professor C.R. Rao and Bhargavi Rao Gold Medals, which is for the MSc students, that is sponsored by our great Professor C.R. Rao. And various Best Paper Awards in association with the WSTA as well as ICSTC, specifically for young researchers and academicians. So I request all of you to please note these things and send in your entries. It's actually wonderful to have so many great professors sponsor these awards for us. So once again, thank you for participating in the forenoon session. Let us break for lunch, and we'll be back at, it's already 1:30. So request all of you to be back at 2:25. 2:20. Okay, thank you.
Something that